Okay, so in the last video we set up what a complex number is, and we took a look to see different ways of expressing that complex number. And I just wanted to talk briefly about the argument of the complex number. So if z is equal to a plus ib, right, the modulus of z is the r, and that's the hypotenuse of your triangle. Where's my triangle there? And so if this point here is a plus ib, then r is the modulus and theta is the argument. Okay, and so the question is how do you actually compute theta? So we know that from the triangle, right, that the tangent of theta is b over a, but you have to be careful, right? Especially if a is equal to 0. And then also, when we invert this, the problem with inverting the transform, inverting the tangent, is that you only get angle measures between, where am I? There am I. So you only get angles between negative pi halves and pi halves. By that I mean, if you take an a and a b and you compute this inverse tangent on your calculator, you're going to get an angle measure between plus and minus pi over 2. Okay, but we may not want an angle between plus or minus 2. We want our angle to be a 4-quadrant inverse. Okay, and so that's what I'm going to talk about now. So the 4-quadrant inverse tangent. By the way, most software packages have some kind of 4-quadrant inverse. I believe MATLAB, for example, has a tan 2, and then you put in your a and your b, and b over b comma a, and it'll compute the 4-quadrant inverse for you. And Maple has a command that's arctan and then b comma a. So if the arctangent has if you give it 2 arguments, right, then it returns the 4-quadrant inverse. Okay, so how do we do this? So the way to think about it is that I would always, when I'm trying to compute theta, I'm always going to consider which quadrant my point is in. Okay, so if I'm in quadrant 1, for example, then I know that my inverse tangent of b over a is going to be equal to theta. So this is quadrant 1. Okay, and then what happens if I'm in quadrant 2, right? So that means that the x-coordinate is going to be negative, or the a is going to be negative. So this is where a is negative, b is positive, right? And so in that case, your calculator is going to give you this angle, right, as a negative theta. And so in order to get this angle, what would you do? You'd add, so in quadrant 2, you would take whatever your calculator gives you, and then you would add pi to it. Okay, and similarly, what happens if you're in quadrant 4 to begin with? Then you don't have to worry. So quadrant 4, theta is just going to be the inverse tangent. But then what happens if you're in quadrant 3? Right? If you're in quadrant 3, then your calculator would give you this angle. And so in order to get this angle, you could add theta, add pi, but because we said that we wanted to get our angles between minus pi and pi, we would subtract pi here. So in quadrant 3, to get angles between minus pi and pi, right, you would take your inverse tangent, and then in this case you would subtract pi. Okay, and so these would give you the values between minus pi and pi. And so the upshot here is not to memorize these 4 things, but to actually, whenever you're looking for the argument of your complex number, plot it first. See where you are. Good. All right. So should we try an example maybe? Find r and theta if we have the following complex numbers. How about z equals minus 3? Z equals minus 3, that's in the complex plane. Where are we? That's 3 plus, or minus 3 plus 0i, right? And so you're back here. And so in this case, your r is equal to positive 3, and your theta is what? In this case, I believe we were keeping pi and not keeping minus pi, so we'll write that as positive pi. Good. All right. How about another straightforward one, maybe that's not too hard to find? Z equals, oh, let's do positive 2i. Okay, where are you? I guess we could use the same. 2i, we're right here, right? And so therefore my r is equal to 2, and my theta is pi over 2. Good. And now how about if z is equal to minus 1 plus I? Then the r is equal to the square root of 1 squared plus 1 squared, which is the square root of 2. And geometrically, where are you? Minus 1 plus I, we're in quadrant 2, right? So again, my calculator would give me this angle, but then I would want to add pi to get that angle. Okay, but of course this one's fairly straightforward to compute, because it's a 1, 1, what's the triangle here? 1, 1, square root of 2, right? So we know that that's going to be minus pi over 4, and so minus pi over, so theta is going to be minus pi over 4 plus pi, which would be 3 pi over 4. Good. All right, so that's how you find the r and the theta for the polar form of your complex number. Okay, so now we want to change gears a bit, and we want to take a look at operations on complex numbers. And so if z is equal to a plus ib, then the conjugate, or complex conjugate, of z is denoted by z bar. So that's read as z bar, and that's going to be a minus ib. So the idea is whatever your imaginary part is, you negate that. Okay, so for example, if z is equal to 3 plus 5i, then the conjugate of 3 plus 5i, which is written with a bar, is 3 minus 5i. Good. If z is equal to, if z is equal to 2, what is z bar? Did you guess? Is it 2? You're right. If you guess that, you are correct. So the conjugate of a real number is itself. Good. Now, what happens if we take z times z bar? That would be a plus ib times a minus ib. And from algebra, we know that that's going to be a squared minus ib squared, because the middle terms will fall out. And so if you compute that, that's going to be a squared. The I squared, well, I'll go ahead and write it as I squared b squared. Replace I squared with negative 1, and we get a squared plus b squared. And so one way of writing the magnitude of z, which is your r, is to write it as the square root of z. Let me see if I can write that again. Square root of z bar. Good. Which is the square root of a squared plus b squared. All right. Now one thing that's kind of handy. Oh, let's wait on that. So far we know how to conjugate, and we know how to take the magnitude. Let's take a look at addition and subtraction, multiplication and division. Okay, now these are all done just like you would perform it on a polynomial. So let's try to, so if I take a plus ib plus c plus id, the way you would compute that is you would take you'd take the real parts and add them together, and then you take the imaginary parts and add them together. Okay. Similarly, if that was a negative sign, then you would subtract the two reals and subtract the imaginaries. Good. And then multiplication, you would do, oh, I guess we just did multiplication, didn't we? Without even realizing it. You would just FOIL this out. Remember FOIL? First, outer, inner, last. So AC plus IBC plus IBD plus I squared BD. Oops, BD. Oops, I got an incorrect term there. That should be an AD there, right? So that's going to be AC minus BD plus I times BC plus AD. Don't memorize that. Memorize or remember that when you do this multiplication, you're just going to FOIL it out. Good. And finally, what happens to, or how do you interpret division of two complex numbers? Well, the idea is that you're going to get we need to get the complex number out of the denominator and make it a real number because we know how to do real division. And so we're going to multiply by the conjugate. Oops. Oops. So I'm going to leave the top. A plus IB. We know how to multiply these now. And so you would go ahead and multiply out the numerator. It's the denominator that's important here because now we're not dividing by a complex number, we're dividing by a real number. And we know what it means to do real arithmetic. Good. So I think I'm going to pause here, and in the next video we'll do a quick example. So if you want to get ahead of that, in the next video we'll start with the example 1 plus 2i divided by 3 minus, let me write it so you can read it. 1 plus 2i divided by 3 minus 5i. Okay?